Rudy's got the chalk zone. Rudy's got the chalk zone. Okay, so we're here, and we've been talking about resistors and some complicated circuits recently. We've talked about Ohm's law and how to dig into those circuits with series and parallels and pull things out. Let's talk about capacitors, because those are a thing, right? So imagine for a second we have a circuit. It's 12 volts. And we have a number of parallel plate capacitors in a row, each one with capacitance C1, C2, and C3. How would we go about adding those capacitors together? Well, what we have to think about is the following. When we put capacitors in series, when capacitors are in series, what is going to happen is they are all going to develop the same amount of charge. And the reason why this is going to happen is if we think about the positive charges moving, thanks Ben, when this gains a positive charge, it's going to create a similar voltage on the other side. So we're going to get that negative charge there. And then what's going to happen is down the line, we're going to get these positives and these negatives. And it's going to happen equally across everything. So in series, all of the capacitors, all the caps, have the same charge. Okay? And by same charge, we mean Q is equal. Okay? That value Q is equal. Now, because of this, if the Q value is equal, and if we take a look at this equation, Q equals CV, this is our capacitor equation. If all the Q values are equal, then the capacitance determines what the voltage drop is across each capacitor. Okay, and we could use this equation, Q equals CV, or if we wanted the voltage drops, like if we were using a Kirchhoff law, we could say that V equals Q over C. But in the case of the series, all the caps have the exact same charge across them. Okay, that is very, very important. Because they all have the same capacity, or the same charge across them, the voltage drops can be different. So the voltage drops can be different here across each of them, okay? Now, in terms of adding these capacitors together to get one capacitor, like 1 mega capacitor, when capacitors are in series, they act similar to resistors in parallel. And what I mean by that is that when capacitors are in series, we actually find the equivalent capacitance of a circuit by taking 1 over each individual capacitor. So this is what we did for resistors when they were in parallel. We treat capacitors in series like parallel resistors, okay? So if we had values of like 10, 20, and 30 here, this equivalent capacitance is going to have to be less than the smallest capacitor. So whenever you actually have more capacitors strung in series together, your capacitance as a whole is going to go down. And I know that sounds weird because it's like, yeah, but I can store more charge. You can't store more charge. That charge is the same across all the capacitors. So your actual capacitance is going to go down in this scenario, okay? If we look at a parallel setup, things are a little different. In a parallel setup, so here's our 12 volt battery again. In a parallel setup, what's going to happen is the charges will not be equal on each capacitor. So if I've got C1, this is C2, and then this is C3, what's going to happen is I'm going to have a charge come out, some positive charge. It's going to run along as the current, and then it's going to make a choice. Which capacitor would I like to go to? Well, none of the capacitors have charge right now, so let's just pick C1. Yay! Because I picked C1, the negative pops up on the other side. Well, now a second charge comes out, runs along the current and says, where do I want to go? Well, it wants to go to the region with the least potential, right? So it can't be C1. That already has a charge on it. I don't want to go there. Someone's living there. So I'll go to either C2 or C3. Bloop. Negative concurrent. Next charge comes out. Where do I want to go? Well, I don't want to go to C1 or C2. They have charges on them. I don't want to deal with that. I'm going to go to C3. Yay! And what essentially happens here is that each capacitor will build up its charge, okay? And each capacitor will build up charge independently of the other ones. What will be the same across all of these is the potential will be the same. Remember, we started at this node point, this junction right here, and we end at this junction right here. The potentials need to be the same now. So when we're in parallel, we're going to find that the voltage drops, these potentials, they are equal. But the charges, Q, can be different on the capacitors. Okay? And once again, we see that just by saying, look, V equals Q over C. If all the voltage drops are equal, then if they have different capacitances here, they're going to have different charges. It's the only way to get that to work. Okay? And that's a very important thing for us. What this means, though, in terms of adding these capacitors together, is that if I put more capacitors in parallel, I could jump more charges onto them. Because if I put in a fourth capacitor right up here, where I've got some space, if I put in a fourth capacitor, well, it doesn't have any charges yet, so I can put some charges there. I could store more charge. And since I can do this, I'm actually gaining capacitance. So for a parallel system, what we find is that the equivalent capacitance is just the sum of the capacitors, just C1 plus C2 plus C3 plus C4. And if you notice, parallel capacitors act very similar to series resistors. Okay, so this is how we can think about these things here. The two big equations we need are here in purple and highlighted. Twink, 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 twink. It is important to recognize what is going on in series and in parallel with capacitors. Series caps all have the same charge, the Q is equal, but the voltage drops are different. In parallel, the voltage drops are equal across the gap source or across the node points, the junctions, but the charges can be different across the capacitors. Okay, so that's a very important thing to recognize there and what's going on with capacitors, how we add them together. If we want to actually include a circuit that has both resistors and capacitors, things start to get pretty complicated. We need to use in some way this voltage drop equation in a Kirchhoff's law, and things get a little hairy for physics too. In order to do this, we'll actually need to go into AP Physics C and employ some calculus. So the next video is an optional one. If you want to do the AP Physics C stuff, you can check that out. But for AP Physics 2, this is all we need to know. So until next time, this is finished. Take it easy. Adios.